Does consciousness come along for the ride? Information and Complexity, Essay 6. It's a tempting idea, isn't it? Consciousness is just what happens when things get complicated enough. In both neuroscience and pop science, we often hear that if a system, like the human brain, reaches a certain level of complexity, something clicks. The lights turn on. It's how people sometimes explain the magic of our minds, and increasingly, how they speculate about artificial intelligence. If we keep building bigger AI models, the thinking goes, eventually we'll get something so complex that consciousness will just come along for the ride. It sounds intuitive. After all, we are complex, and we are conscious. But there's a problem with this idea. The scientific evidence to support it isn't really that clean. So what's really going on here? To find out, let's follow the science and ask 3 questions. 1. What does the neuroscience say about the link between consciousness and complexity? 2. Where does the data start to break down? And 3. Does consciousness come along for the ride when systems become appropriately complex? Question 1. What does the neuroscience say? When it comes to consciousness, there's no shortage of scientific theories. The last time I checked, there were 22 of them. And as you might expect, the scientists behind those theories don't tend to agree on very much. In fact, they disagree on a lot. What consciousness is, how we should measure it, and where in the brain we might find it. But in the middle of all of this disagreement, there's one idea almost all of them seem to agree on. Consciousness has something to do with complexity. There's probably a good reason for this consensus. It's backed up by decades of research showing a strong relationship between brain complexity and conscious awareness. The findings come from all kinds of brain imaging tools too, and all kinds of definitions of both consciousness and complexity. And yet, the pattern is remarkably consistent. When the brain's activity becomes more complex, consciousness tends to be present. When complexity drops, awareness often fades. I know what you're thinking. Those are some slippery words you're using there, Susie. What exactly do you mean by consciousness, and how are neuroscientists measuring complexity? Great questions. I am glad you asked. In neuroscience, a common way to understand consciousness is to split it into 3 categories. 1. States of consciousness. This is like being awake, asleep, in a coma, under anesthesia, or tripping on psychedelics. 2. Contents of consciousness. The specific things you are aware of in any given moment, like a face, a sound, a memory, or the color red. And 3. Self-consciousness. The sense that you are the one having those experiences. In this essay, let's just focus on the first 2. To test for states of consciousness, scientists might ask whether a person can follow simple commands like squeeze my hand. For contents of consciousness, they might ask someone to respond to a specific stimulus. For example, press a button if you see a house. We use tools like EEG, MEG, fMRI, or TMS to record patterns of brain activity while asking these kinds of questions. That way, we can compare what the brain looks like when someone is consciously responding and when they're not. These patterns are known as neural correlates of consciousness, or NCCs. And yes, they are controversial, but let's leave that can of worms for another day. Complexity, meanwhile, is also measured in a bunch of ways, but almost all of them come from information theory. Some use Shannon entropy, and others look at how easily brain signals can be compressed, something similar to algorithmic complexity. The general idea is that more complex signals are less predictable. They're harder to summarize and they're harder to compress. Take sleep, for example. When we are in deep non-REM sleep, when dreaming is rare, EEG signals tend to be slow, repetitive, and highly predictable. These are the big rolling brain waves known as delta waves. But when we are awake, the brain's electrical activity speeds up. It gets messier and more varied and harder to predict. Now imagine running both sets of EEG data, sleep and awake, through a compression algorithm. The sleep data, with its repetitive patterns, is easier to compress. The awake data, full of variation, takes up more space. In other words, the file size of the awake brain is bigger than the file size for the sleeping brain. So we say the brain signals we find during sleep are less complex than the ones we find when we are awake. Most of the research linking complexity to consciousness has focused on states of consciousness, those broad conditions like being awake, asleep, anesthetized, or in a coma. The findings have been so consistent that complexity measures are starting to show up in clinical settings too. Some doctors have used them to help distinguish between patients who are in a vegetative state and those in a minimally conscious state, conditions where a person might appear unresponsive but still retain some inner awareness. But the link between complexity and consciousness doesn't just show up in states of consciousness. There is also evidence that complexity tracks the contents of consciousness too. In one clever study, participants watched a short film, played forward and backward. The visual input was identical in both cases. They were the same scenes, the same colours, and the same lighting. But only the forward version makes narrative sense. The researchers found that brain activity was significantly more complex during the forward viewing than the backward one. Using dozens of different complexity measures and a wide variety of brain imaging techniques, the same pattern keeps showing up. Complex brain activity tends to go hand in hand with conscious experience. Question 2. Where does the data start to break down? If this story sounds a little too neat for neuroscience, you are right to be suspicious. It is true that complexity measures usually rise with consciousness and drop when it disappears. That is a robust finding, and there have been hundreds of studies. But it's not the whole story. The story is complicated in a few ways, but let's focus on the fact that there are exceptions to the usual. Sometimes complexity measures go up when consciousness measures go down. For example, with seizures. During a seizure, the brain doesn't go quiet. It floods with activity. Neural signals become overactive, disorganized, and unstructured. It's kind of like the brain goes into chaos. Most complexity measures score that activity as highly complex, but consciousness often disappears. And then there are psychedelics and certain dissociative anesthetics, like ketamine. These drugs could be described as warping consciousness. People are conscious, yes, but they often report vivid hallucinations, distorted time, and out-of-body experiences. Complexity measures tend to be high, but conscious experiences are clearly altered. So what is going on? It might be helpful to distinguish between two things: complexity as whatever our complexity measures are measuring, and complexity as the thing we actually think of when we talk about complexity. Let's call the first kind measured complexity and the second meaningful complexity. Ideally, our measured complexity would capture meaningful complexity, but that's not always the case. As I mentioned above, most complexity measures in neuroscience come from information theory, things like Shannon entropy and compression algorithms. These tools are great at picking up on structured variation, when structure is there to be found. But they run into trouble when there's no structure, when the signal is distorted or random. That's because both randomness and details are hard to compress. They both show up as high complexity on these measures. Even though one is chaotic noise, and the other is a meaningful pattern. So, what about meaningful complexity? There's an interesting relationship between disorder and meaningful complexity. As disorder increases, complexity tends to rise up to a point, but then it flips. It hits a peak. As disorder keeps rising, complexity starts to fall. That tipping point, where complexity is at its maximum, is often called the edge of chaos. You can see last week's essay for a deeper dive into that idea. You can think of this complexity curve as having two sides. On one side, increasing disorder leads to more complexity. This might be where most brain states sit. When we're awake and aware, we might be closer to the top of that curve. But during deep sleep, coma, or anesthesia, we might slide down that slope. On this side of the curve, disorder and complexity rise and fall together, and the relationship holds. But on the other side of the curve, past the edge of chaos, disorder keeps increasing while complexity begins to drop. States like seizures or psychedelics might be examples of the brain operating on the far side of the complexity curve, where disorder keeps rising, but complexity starts to fall. It might be that straying too far in either direction, too ordered or too chaotic, is what causes consciousness to fade. The brain may need to live in that narrow band near the edge of chaos to sustain awareness. We don't know for sure, but that explanation would fit the findings. From this, it might be tempting to conclude that the edge of chaos is the key, that if a system gets itself close enough to the edge of chaos, then consciousness will just show up. Question 3. Does consciousness come along for the ride when systems become appropriately complex? Well, not quite, and for a few reasons. First, not all highly complex things are conscious. Take the cerebellum. It's that small, wrinkly structure tucked under the back of the brain. It's one of the most neuron-dense, intricately wired parts of the brain. By almost any measure, it would be considered highly complex. So, if consciousness simply comes along for the ride when complexity gets high enough, you'd expect the cerebellum to be one of the brain regions that contributes the most to conscious experience. But it's not. People with damage to the cerebellum, or those who are missing large parts of it, can still have completely intact conscious experiences. The cerebellum is complex, yes, but apparently not in the way that matters for consciousness. Second, complexity and consciousness may be correlated, but that doesn't mean one causes the other. Let's start with a simple example. Say every time we saw someone opening an umbrella, we also saw wet sidewalks. If we didn't understand weather, we might think umbrellas cause the sidewalks to get wet. If so, we would be mistaken. Really, there's a third thing happening: rain. Rain causes both the umbrellas to go up and the sidewalks to get wet. The two are correlated, but one doesn't cause the other. Rain is a hidden third variable that explains both. But our error might not stop there. If we only conducted our research on the relationship between umbrella use and wet sidewalks when it was raining, we might think that the correlation between umbrella use and wet sidewalks was rock solid, unbreakable even. But we would be very wrong, because in many parts of the world, people use umbrellas on sunny days too, for shade, not rain. Umbrellas go up, but sidewalks stay dry. So what does this have to do with the brain? Well, almost everything we understand about consciousness comes from studying humans, and to a lesser extent, other animals. We've mostly looked at complexity and consciousness in systems where we already assume consciousness is present. So, It's no surprise that we keep finding a correlation between complexity and consciousness. But that's a bit like studying umbrella use, only when it rains. If we're only looking at human brains, one specific kind of system, we might be overestimating how universal that complexity consciousness link really is. Just like the relationship between umbrellas and wet sidewalks, there could be a third thing happening, a particular kind of architecture or dynamic mechanism or function that is behind both consciousness and complexity. If that is the case, complexity and consciousness might just be co-travelers, like umbrellas and sidewalks. So, what could this hidden variable be? Most theories of consciousness seem to agree that there is a sweet spot for the brain. They don't usually call it the edge of chaos, but the idea is similar. A balance between too much rigidity and too much randomness. Consciousness seems to need just the right amount of tension in the system. Where the theories seem to differ is how they think the brain keeps that balance. Integrated Information Theory, or IIT, calls it integration and differentiation. Global Workspace Theory, they talk about global broadcasting. Predictive Processing Theory describes the constant dance between expectation and surprise. And Recurrent Processing Theory focuses on the difference between feed-forward and feedback loops. Even the more speculative ideas, like electromagnetic field theory and quantum theories, think the system needs to stay in dynamic balance, not too simple and not too chaotic. On almost every one of these mechanisms, today's AI falls short. Let's take large language models like ChatGPT. They can simulate language, reason through problems, even hold a conversation, but they don't have any of the balancing mechanisms that these theories of consciousness see as essential. They don't self-regulate. They don't respond to surprise in any adaptive way. They don't coordinate across modules or self-stabilize their own perceptions with feedback. By the standards of any of these theories, they're missing the thing that counts. They may be complex, but not in the way that seems to be required for consciousness, at least according to these theories. So, where does that leave conscious AI? According to most consciousness theories, just adding more complexity probably isn't enough. Consciousness might need, or simply be, specific kinds of structures, architectures, dynamics, and functions. So, if we build an AI like that, would it have conscious experiences? Maybe. Of course, it's possible, perhaps even likely, that all of those theories are wrong, or at least incomplete. Maybe consciousness isn't simply feedback loops, or integration, or predictive models. Maybe. Next week, how much information do you think it takes to build a building? A lot, right? We need blueprints, plans, sequencing. The entire structure has to be laid out in advance before anything can take shape. In that sense, a blueprint holds a lot of information, everything needed to make a building. But what about life? How much information does it take to build that? Well, there's no master diagram for an oak tree, no detailed layout for a brain. All we seem to have is DNA, and yet somehow, from this simple code, we get the most complex thing in the known universe. What kind of information is that?